4 chapters. I think I'll throw 14 on the next exam. Okay, other questions? Uh-huh.
What chapter would be the homework for exam 3?
It would be 10, 11, 12, and 13 we would do. Okay. Any other questions? Regarding the nomenclature retake, I was planning to do that coming up here today, but are you guys ready for the nomenclature retake?
We should do that tomorrow.
Well, tomorrow might be tough.
How about Wednesday?
We could do it Wednesday, but it would have to be timed on Wednesday.
What if we don't do it?
Yeah, you want to do it because you lose points. Are you afraid that it's going to be worse than before? Or? As long as you do, huh?
I just don't want to take a test.
Oh, right. I know some people had prepared. They're ready to go today. All right. Uh-huh.
After 11 more problems, do we also have to do these?
The quantum, yeah, you should do those quantum ones, but I'm not going to collect those. The answers, the answers to the supplement problems are in the supplement itself. Yeah. But yeah, you should do those. You should do those because the problems in the book don't get quite to the level that's required. I'll talk more about the exam as it gets closer. All right, just one last thing about the quantum here, the way the periodic table is organized. Over here on the left, we have the alkali metals, the first column here. And one characteristic of the alkali metals is they're very reactive. They all have low ionization energies. So they easily react with things like air and water, quite violently actually. And so these are the alkali metals reacting with water. Water we don't normally think of as a very strong oxidizer. And in fact, it's a very weak oxidizer, but you don't need a strong oxidizer to oxidize the alkali metals. And so in nature, we don't find like sodium deposits. We find sodium ion in like salts. But if we have sodium metal, it behaves quite a bit differently. It's just too reactive to exist. And so any sodium metal that we use has to be synthesized. What they do is they take the sodium ion and give it an electron to form sodium metal, and then they protect the sodium metal from exposure. They either submerge it in mineral oil so it can't come into contact with water or air, or they put it in like a nitrogen or argon atmosphere that doesn't have any moisture or oxygen present. Otherwise, it just oxidizes way too fast. So these metals are what we call highly reactive metals. There are also metals that react with acids. Those are called the active metals. Most of the metals react with acids, except like the coinage metals, gold, silver, etc. Regular acids, you might need a more powerful acid to react with those. And then over here we have on the right the halogens, like chlorine, bromine, iodine. These all want one more electron to complete their octet, and so these are all good oxidizers. Chlorine's a much better oxidizer than bromine. Bromine's better than iodine. It has to do with size. When we're on this side, smaller is more reactive. So chlorine's smaller, it's more reactive than bromine. which is more reactive than iodine. So iodine is a very mild oxidizer. You know, they used to, when I was younger, you know, we used to have hydrogen peroxide for wounds. So hydrogen peroxide turns out to be too strong of an oxidizer. And so now they have like iodine type solutions, which are much more mild oxidizer. You know, you wouldn't want to use bleach for your wound because, you know, chlorine. Actually, bleach is chlorine with a +1 charge. This is just chlorine, which is quite reactive. Anyway, this is chlorine with phosphorus. All these are reacting. This is iodine with zinc reacting, but you can see it's quite a violent reaction. Phosphorus is not the greatest reducing agent there is. If you react chlorine with lithium, or chlorine with sodium, or chlorine with potassium, you're going to get a much, much more violent reaction, more explosive than this. But over on this side, the smaller, the more reactive. So if you're an oxidizer, the smaller you are, the more reactive you are. However, over on this side, the bigger, the more reactive, because if you're losing electrons, you want to be bigger. And so when we talk about reactivity, we can't always look at one side of the equation. That is, when we're looking at activity series, something like potassium is going to be more active than sodium. We should be more active than lithium on the activity series side. But that's for something that's losing electrons. For something that's gaining electrons, yeah, chlorine is going to be more active than bromine, which is going to be more reactive than iodine. And so reactivity, we always look from the perspective of the type of reaction we're considering. And so if we're considering like losing electrons, or if we're considering gaining electrons, it's a big difference in terms of how size impacts that. But and then we just divide, you know, we have the transition metals and the bond. So these are the most common, you know, the alkaline earths are a little less reactive than the alkali metals. The halogens are quite reactive. The noble gases are totally unreactive, the transition metals. And then down here we have the lanthanide and actinide, which are kind of like the transition series here. As we're filling inner subshells, you know, inner subshell electrons or inner electrons. So the power, the projector wasn't working last time, so let's just take a look at chemical bonding before. What this chart is showing is just the octet rule. Like, for example, nitrogen. Nitrogen can either gain 3 electrons or can lose 5. Typically, losing 5 is a lot, so common charge for nitrogen is +3, +5, and -3. The +3 is still difficult, so you don't normally see a nitrogen 3 ion. You know, it's too unstable. So that +3 charge is stabilized with oxygens and other species to form a polyatomic ion. And so we don't see monatomic ions. However, nitride we do. Nitride can be a monatomic ion with 3 extra electrons and 3 minus. Here we see it in terms of the Lewis symbol. Lewis symbol for nitrogen. Let's see. Or maybe I could just do it on this here. The Lewis symbol for nitrogen is shown here. And it shows 5 dots. We have the 5 dots because there are 5 valence electrons, and the valence electrons are the highest end. So when we look at the highest end here, it's 2, and we sum up the total number of electrons. So we have 2 in the 2s and 3 in the 2p. But what we're going to do is we're going to combine those to get a total of 5 electrons in the highest end. And then we'll show it like this. Here it kind of looks like a pair here and 3 singles like you'd expect, but this has no relationship to, it doesn't have to have a relationship to how many unpaired electrons and how many paired electrons we have in the energy level diagram. But here it does coincide. We can gain 3 because it will take 3 electrons to fill up that shell. So the p subshell can hold a total of 6 electrons in the 3p orbitals. And so that's the 2p6 here. Now we have a first shell that's filled and a second shell that's filled, and that's the octet. And so this is the Lewis symbol for the nitride ion. This is the symbol for nitride as well. All right, so for oxygen, which we did the other day, this is 2 electrons short. So to get its octet, this would be the Lewis dot symbol for the octet around oxygen. The core electrons aren't shown, so the 1s2 are in there, but they just aren't shown in this. Fluorine's just 1 electron short. Fluorine's the smallest of these 3 here. And so fluorine being the smallest would be the most strongest oxidizer out of this group. Fluorine would be stronger than oxygen. Oxygen would be stronger than nitrogen in terms of that. But fluorine only needs 1 electron to get the octet here. Neon doesn't want any electrons because any extra electrons that neon would take would have to come from its filled second shell. That's not favorable. Break up that shell. So neon's very unreactive. That's why we call them noble gas. Noble gases used to be labeled inert gases because they're so unreactive. They still could be labeled inert gases. You know, there are some exceptions to that. Xenon reacts, etc. And so some noble gas compounds were formed. On the other side of the periodic table, it's easier to lose electrons. So over here, if we look at sodium, the first shell's filled, the second shell's filled. We just have 1 electron in the outermost shell, which is the n equals 3 shell. So there's 1 dot here representing that 1 3s electron here. If we lose that, then we have the neon configuration, which is 1s2, 2s2, 2p6. And that's losing this single dot here. Now, normally what we do with this is we don't normally write it like that. Let me show you. Did I say, is this in? When we do Lewis drawings for charged species, we normally write it like this, where we enclose it in square brackets and then write a positive sign there. So this is showing that sodium's lost its valence electron and now has a positive charge. So this is the Lewis symbol. This is just the regular symbol for sodium. Here, magnesium has 2 valence electrons, which we can lose without too much difficulty with IE1 and IE2. I mean, it's still going to cost energy, but the payback comes in bonding. So that's what magnesium would look like. Aluminum has 3 valence electrons. We can lose all 3, form the aluminum ion, which would have this. And so these are the Lewis dot symbols or the Lewis symbols. For the sodium ion, the magnesium ion, and the aluminum ion here. You know, these footnotes are always important to read. A lot of people don't read figure captions and footnotes. But they're always good to read. So we already know this pretty much. I mean, over on the right, it's easier to gain than to lose. Over on the left, it's easier to lose than to gain. These are all the fixed charge ions. Beryllium's also fixed charge at +2, but beryllium's so toxic they've left it out here. Boron's not that common, +3, as a +3 cation, but it's common as an element in different compounds. You know, boron's much more kind of non-metallic than metallic. You know, boron is on the line. This is the dividing line here between what we say metals and non-metals. You know, would be here. this zigzag line. Oops, I guess it encapsulates boron here. So boron falls into the, not the metal camp, but the non-metal camp here. And so it doesn't form an ion like aluminum does. It forms molecular compounds, typically, for boron. Aluminum, even though it's right on the border here, so it's a semi-metal, it's more metal-like. I mean, aluminum has much more of the characteristics of the metal, whereas boron has more of the characteristics of the non-metals here. Here. When we draw the Lewis structures for ionic compounds, they look like what we had drawn earlier in the class. And so if I wanted to draw the aluminum oxide structure, it's going to look something like this. We're going to have oxide and aluminum ions. In a lattice, and we're going to have 2 aluminums and 3 oxygens. Since this is a 3-dimensional lattice, where I draw it, it's just going to continue on, and so in 2 dimensions plus the third, which would just be coming out of the board here, and then going in the board here. So I'll just build up a crystal lattice like this. The bonds are not shown by any kind of line. When we share electrons, we usually show a line, but in an ionic bond, we just write the ions next to each other. And what this symbolizes is something like this, is what we visualize when we're looking at something like this. We visualize an aluminum ion. Aluminum ion's tiny. When you lose 3 electrons, you shrink. When you lose like 1 electron, you shrink to about half the size. So let's say you're like 5 feet, and then you lose an electron, you're down to 2.5 feet, something like that. And so and then you lose more electrons, you shrink. It's not, you don't shrink to again half the size, it kind of levels out. And then the oxide is quite a bit bigger, because when you gain electrons, it's hard to hold on to those electrons because the number of protons doesn't change. So oxygen still has the same number of protons, which is 8 protons, but now has 10 electrons, so it has to hold on to a total of 10 electrons, 2 core electrons and 8 valence electrons with only 8 protons. So it's harder to do. And so when aluminum, for example, we go from aluminum metal to aluminum 3+, the size dramatically decreases. And when we go from oxygen, oxygen should in fact be kind of small, to oxide, the size grows considerably, like doubles in size. And so this size gets cut in half. I did a little bit more than half because it's +3. This I did a little bit more than double, but it just about doubles. It doesn't really matter if you add a bunch more. But what this is supposed to represent is we got an aluminum ion there, and we have these oxides that are trying to bond to it like that. And some lattice. These are supposed to be round, not oval shape.
For the inside Lewis symbol or Lewis structure, the electrons are open circles. It doesn't matter if it's like a closed circle.
No, it doesn't matter. It doesn't matter. It's just if I did closed circle, it just takes more time. And so this is what we call the Lewis structure. When we have ionic bonds and we have a crystal lattice. This is the start of the crystal. This would be an extremely small crystal. If we want to build a bigger crystal, we just add more. So if we have aluminum here, how many oxides do we want? We want as many oxides around that as possible. And if we have an oxide, we want as many aluminums around that as possible. And so just build up a structure like this. Oops, I wasn't supposed to put those dots there. Now, there are, in these lattices, you're thinking, wow, these oxygens are like touching each other. They don't want to touch each other because they're negative. And so in a lattice like this, there are both attractions and repulsions. What we have to have is we just have to have the attractions be stronger than the repulsions, and then the lattice will be held together. If the repulsions exceed the strength of the attractions, then the lattice is going to fall apart. And so, yeah, these oxides are really close to each other, but the aluminums are keeping them together. And so, just as long as the attractions are strong enough, we're all right. And so this is an example of an ionic compound, of course. We need the combination such that these ionic compounds are going to be electrically neutral. The bonds in an ionic crystal are very strong, bonds, which is why nearly all ionic compounds are solids at room temperature. In fact, can you think of an ionic compound that's not a solid at room temperature? I can't think of one unless it's quite exotic. Solid, what's the significance of solid? Solid just means relatively high melting point. And the stronger the bond, the higher the melting point. Because when you melt it in a crystal like that, you have to break apart the bonds. And breaking apart the bonds is going to take a lot of heat, a lot of energy if the bonds are strong. So aluminum oxide this stuff is nearly impossible to melt. I mean, the bonds are so strong. Other ionic solids are a lot easier to melt, like potassium chlorate. I was able to melt with a Bunsen burner. Just took less than a minute to melt that stuff. And that's because the chlorate ion is kind of big, and it's only -1. And potassium is also kind of big, and so the ionic bond is not as strong. What makes a stronger bond, ionic bond? Well, what makes a stronger bond is a higher charge density. We want, higher charge density makes stronger bonds. Higher charge density just means high charge, small size. High charge, small size. So it's the charge to size ratio is what this is. Charge to size ratio. If you do melt it, you get a liquid ionic compound. And molten compounds, molten salts, liquid ionic compounds are called molten salts. Molten salts are good conductors of electricity because we have that translational mobility. So we did the demo with potassium chlorate liquid in lab. And that lit up the light bulb quite brightly. That was a lab demo. The reaction of sodium metal and chlorine is quite violent. So what they did is they put a chunk of sodium metal in here and added some chlorine gas. And you could see it's quite violent, but fortunately not explosive. Otherwise, you wouldn't want to do this if it explodes in your face. This is Erlenmeyer, glass Erlenmeyer flask, which we don't. But there's lots of videos of this reaction. It just ignites, and you get this bright, intense light. And then you could see crystals of sodium chloride up here. And, here's the reaction here. So, for example, sodium here has, this is the most common isotope of sodium. There's 11 protons, 12 neutrons. This would be sodium 23. The average mass of sodium is around 23. It's 2299. So this is by far the most. In fact, I think sodium only has one naturally occurring isotope. How can you tell? How you can tell is we have to go to a table of isotopes. The table of isotopes is, I think, in chapter 2. But it could very well be that sodium just has one. If it has multiple, then for sure sodium 23 is most abundant. We can look at the periodic table and tell how many isotopes there are and which one's the most. Well, we can kind of figure out the most abundant. It's got to be close to the weighted average there. But look what happens to the size. When sodium loses one electron, then we have 10 electrons total, but we have 11 protons still. And the 11 protons are going to pull in the electrons closer. Not only that, we lost the electron out of the third shell. So if we lose the electron out of the third shell, then we're down to the second shell here, which is going to be quite a bit smaller. And so the sodium ion shrinks. But look at what happens to the chlorine atom. The chlorine atom just gains one electron, but it still has the same number of protons, 17 protons, but now 18 electrons. Its size just grew, like doubled. And so here, the cation here, it's about half the size, and the anine's about double the size. And so, we come up with a general rule. The general rule are, and there are some exceptions, just a few exceptions on this, but the general rule are anions are bigger than cations. With a few exceptions, but we're not going to bother memorizing those. Those are the ones with the very biggest cations, which would be like cesium plus or francium plus. Are still fairly big. And so here I can tell, the sodiums are the gray because those are smaller, and the chlorines are green because those are bigger. Here I have my ionic lattice. The ionic lattice doesn't have a definitive end to it, so you can have small crystals or you can have big crystals. And this just extends in 3 dimensions. So what's shown there would be a crystal so small you wouldn't be able to see it. If it only had this many ions. Here. The smallest unit of sodium chloride you could have is what we call a formula unit. There's no molecule here because there's no set unit. For example, if you pick this sodium, which of these chlorines belongs to it? Well, any of them. So we could call this a formula unit, or this a formula unit, or that a formula unit. And so a formula unit is the smallest unit, and we don't call it a molecule in that sense, because a molecule, it'd have one chlorine that belongs to it. And all the other chlorines do not, but in this case, they all belong to it. What happened to them? So what we have here is different views of this. We don't represent the bonds with a line like this for ionic bonds. This line just shows the connectivity. So if I pick, let's pick a chlorine that's stuck inside the lattice here, and I look at how many sodiums it's attached to, I can count 6 of them because of the lines. The lines just show the nearest neighbor. But we don't show ionic bonds like this. This is just shown, this is the way we show ionic bonds. We just put the positive next to the negative. We put as many negatives around the positive as we can, and we put as many positives around the negative as we can. And so this is just an expanded lattice, and it's just showing how things are connected here. But the bond itself is just writing the 2 ions next to each other like this. That's the bond. How many ion bonds are there? There's 6. 1, 2, 3, 4, 5 goes in, and if this were inside, there'd be 6 because there'd be another sodium here. But this is surface. The surface, unfortunately, they don't get to bond as much. This is why, like, things like this, you know, if you're going to dissolve a sugar cube, you know, do all surfaces, and we call this edge, and this is the corner, dissolve at the same rate. And so if you ever dissolved a sugar cube, do you notice what dissolves first? The face, we call it, the edge, or the corner? The corner. You know, what happens is the corners start to become rounded. Why? Because those are the ones that are easiest to pluck off. You know, because if you look at how many ionic bonds does this guy have, it only has 1, 2, 3. That's it. Whereas if you were inside the lattice here, it'd have 6. And so what we say is that the ones inside the lattice are much more stable, the most stable. Then the face ones, and then the corner ones, and the least stable are the edge ones. Those are the ones that are you're gonna lose first in any reaction or dissolution. It should be a physical process. Here's some molten salt. That's probably molten potassium chlorate there. It's liquid salt. Now, ionic bonds work great for ions, but sometimes we don't form ions. So hydrogen can fill its octet with 1 electron, and one way it can do that is to try to take the electron from another hydrogen, but it's going to be unsuccessful. You're going to get in a tug-of-war here. So this hydrogen is trying to take this electron, and this hydrogen is going to try to take this electron, and what results is a tie. What results is a tie, but it still forms what we call a duet. In order to fill the first shell, we don't want an octet. The first shell only needs 2 electrons to fill. So this hydrogen has a duet, and this hydrogen has a duet. So as long as they share, then each hydrogen comes out okay. Share. Or if we show 1 pair of electrons shared, that's what we call a covalent bond, a single covalent bond. Here. Oops, those are supposed to be round, but didn't quite come out. And so this is sharing. And so when we have a covalent bond, we can't transfer the electrons from the reducer to the oxidizer. And instead, what has to result is a sharing scenario like that. Now this is going to form molecular compounds. Ionic compounds are quite a bit different here, but this molecular compounds is what results when we share. I don't know, this is out of order, but this is aqueous sodium chloride here conducts. This is sugar, sucrose. Sucrose doesn't conduct electricity. And this is pure water over here. So let's look at the covalent bond in more detail. Covalent bonds, there are different ways we think of these. The electron cloud or charge density formed by two electrons is concentrated in the region between the two nuclei. So how does a covalent bond hold the atoms together? And this whole idea of orbital overlap, this is called valence bond theory. This is all part of quantum mechanics. Valence bond theory is the partial quantum mechanical treatment. I'll just say quantum mechanical QM treatment. There's another theory which is called molecular orbital theory. Molecular orbital theory is the full quantum mechanical treatment. For the bond. Now, valence bond theory describes the bond as being overlap of atomic orbitals. So bond equals overlap of atomic orbitals. The atomic orbitals, we have the S, the P, the D, etc. Those are the atomic orbitals. In MO, we have new orbitals that form. These are called molecular orbitals. Essentially, the bond is an electrical attraction here. And so this is a hydrogen atom over here, this is a hydrogen atom. And what are these blue dots called? Electron cloud, right. That's an electron cloud. This is for 1s orbital here. You know, the electrons here. If you bring these two together, then what we have is we have overlap of the two 1s orbitals. And so I'm going to draw in the, what would this be called here? Yeah. Does the 95% border capture all the dots? No. And then I'll draw another 95% border here. And then what we see in the atom is we see these two 1s orbitals overlap like this. And when the two 1s orbitals overlap, do you see the density of dots here is much higher in what we call the internuclear region. Internuclear is the region between the two nuclei here. Actually, this is not right. I was looking at that. It should be like that. So we have a much greater density of dots here. And that means there's greater negative charge here from the electrons. The electrons are negatively charged, so we're going to have greater negative charge density.
RGB is charge over size, correct?
Charge over size is the charge density, right? For an atom, but we think of charge density in different ways. In this particular volume here, since you have two, you have this electron cloud and this electron cloud now overlapping, then we're going to get twice as many dots here. And so if we have more negative charge here, that's going to pull the two nuclei into the internuclear region. And so the negative charge concentrated here holds the two atoms together. That's what we call a covalent bond. This is different than an ionic bond. In an ionic bond, the atoms are charged. And since they're charged, or the ions are charged, it could be polyatomic as well. That's what's going to hold them together. Here, the hydrogens are neutral, and so what holds them together is this greater concentration of dots here, negative charge. And so I have my 1s orbital here, 1s orbital. We call this a 1s bond. We call it 1s sigma bond is what it's called, but I don't know if we're going to get into sigma and pi, but this is called a sigma bond. A sigma bond is when we look at the internuclear axis. The internuclear axis is just this axis that we can draw between the two nuclei. Here, let me go with green. If I draw an axis between the two nuclei, and the overlap occurs along this axis, then it's a sigma. Sigma has the overlap occur along the internuclear axis. Sometimes because of the shape of the orbitals, the overlap might not occur on the internuclear axis. So for example, if I try to overlap two p orbitals, I would get a little different thing. And so here, if I have an atom A, let's call this, and this is a p orbital here. This is one orbital, and an atom B, this is a p orbital here. And then if I overlap these lobes and these lobes here, and then I look at the internuclear axis here, the internuclear axis is going to be here. In this case, the overlap is going to be primarily above, up here, and below, as I move these two orbitals closer to one another. Above and below the internuclear axis. And this one is called a pi bond. We have two types, a sigma and a pi. So this would be a pi bond. When I look at the internuclear axis, the cloud is above and below, not along. When I look at the internuclear axis on the sigma bond, the cloud is along the internuclear axis. But even if it's not along the internuclear axis, what happens is it's still an attractive force. So for example, here, A is going to be attracted to this region up here, and B is going to be attracted to this region up here, and the region down here. And so the net effect of this is the two atoms, A and B, are going to be drawn towards each other. Whereas here, they're drawn straight towards each other. They can't get too close, because if they get too close, then the nuclei begin to repel. There's a balance between attraction and repulsion. So if you try to push these in too far together, then the two positives are going to see each other much more. And they aren't going to be shielded by this cloud here. The same thing happens with that. And so there's going to be an optimal distance where you maximize the attractions and minimize the repulsions, and that's called the bond distance. Fluorine really wants to oxidize something. Fluorine's an extremely powerful oxidizer, but it can't oxidize itself. So in this case, the two fluorines are going to have to come up with a tie, and so we wouldn't expect this. Would this be expected? So for example, one of the fluorines is the winner, and the other fluorine is the loser. Does that make sense to you? No. This wouldn't make sense. This would be unstable. And so, even though fluorine's a very powerful oxidizer, it's not going to be able to oxidize itself. But it wants an octet, and it can gain an octet. And when we do octets, we have to double count. The fluorine wants the electron all by itself, but it doesn't get it, as it ends up having to share. And so we end up double counting it, but double counting is okay. Let's go with blue. Which would be that blue region there. I mean, the green region there is where we're going to end up sharing. Sometimes people get lazy, and so this is shorthand way of doing it. It's not real shorthand, but the dots are there. Shorthand, dots not shown. But are there. So you do the shortcuts after you learn the long way. And so we're going to always draw the dots. We're going to do it the proper way. Once you get it advanced enough, then you can do it this way here. We have lone pairs and bonding pairs. Lone pairs are a pair of valence electrons in a molecule that are not used for bonding. And then, of course, bonding pairs would be pairs of electrons that are actually used for bonding, and so versus bonding pairs. So if we go back over here, there's only one bonding pair here, and that's these electrons here. That's the bonding pair. But there are 3 lone pairs on each fluorine. The 3 lone pairs are missing here, and all we see is the bonding pair, as well as the 3 lone pairs are missing on this fluorine, but they're there. Here, everything's shown. The 3 lone pairs on each fluorine, and the 1 bonding pair shared between the 2 fluorines. We have the octet rule. This is for second shell and higher. Second shell and higher. For first shell, we don't need an octet. For first shell, there's only 1 orbital, the 1s orbital. There, we just need the duet, and so we'll have the duet rule for first shell. But the other shells will need the octet. Now, we can see that to fill up the here, we would need how many more? Well, to fill this up, we just need to fill up the
5 more?
yeah, 5 more, 4 more, 3 more, etc. But what if we have the 3Ds in there? Is it the same? And so for gallium, which has argon 4s2, 3d10, 4p1, would be the same. It would be the same. And so this one is going to be the octet rule as well. The 3d10 is a filled subshell. And so all these would need 5 more, 5 more, 5 more to fill up the shell. 4 more, 4 more. 3 more here, built the shell. For zinc and copper, it'd need a lot more. For zinc and copper, it'd need too many to fill up, and it's not going to. And so here, it needs 6 more electrons. And that's way too many for zinc to hold on to. And so for zinc, it's going to lose, but it'd have to lose too many. So we go from 30 to 36, that's 6 electrons, but on the other hand, we go from 30 to 18, we'd have to lose 12 electrons. Losing 12 electrons is just not going to be feasible. And so for zinc, it has to reach some simpler compromise. For zinc, how many valence electrons are there in zinc? Two, and we're going to lose those. The 3D10 subshells, filled subshells, is not going to react. It could, we could take maybe one of them out. That would work. Like, for example, in copper. How many valence electrons does copper have? One. And so you consider copper plus 1 to be fixed charged and the only charge, but copper plus 2 happens. And copper plus 2 is going to screw up the 3D10 subshell. Because all of a sudden somebody took a half a bite out of your cake. You had your cake that you were saving or whatever. And now a half a slice is missing. Well,
Right, let's go. Well, how many electrons are there?
Two. Yeah, so cobalt plus 2 is fine. Here, the reason why we have 3D9 is that it turns out losing that half slice is beneficial when we look at additional aspects of the bonding of this. And so there are reasons for that. But for cobalt, cobalt you'd expect maybe plus 2, maybe plus 4, but plus 4 is too high of a charge. It would seem to make sense at plus 4 because that gives us half filled, 3D5. But it ends up being just losing these, that's a plus 2, and if we go to cobalt plus 3, it's just losing one of these Ds. And so we have, in the D subshell, we'd have 4 singles and 1 paired still left. And you'd think you could take that other paired, but turns out it's too difficult to do. And so we have the octet rule and the duet rule, which works pretty well. And then let's talk about polar versus nonpolar covalent bonds. The bonds that I've shown so far are nonpolar. This is when you have a tug of war and both opponents are equal, so it results in a perfect tie. However, in a polar covalent bond, you have a tug of war, but one of the opponents is stronger than the other, and so it's not a perfect tie. That is, one gets more. However, the other one's not a complete loser. And so let's take a look at 3 scenarios here. Three scenarios would be something like this. What's the strongest oxidizer on the periodic table? Fluorine. And so fluorine wants to take electrons. And then what do you think is the best reducer on the periodic table?
Francium and cesium and bromine.
Yeah, let's go with cesium. Cesium big. Really easy to oxidize. And then we're going to take just a single fluorine. Fluorine's tiny compared to that. Just take a single fluorine like this. And what's going to happen is the fluorine's just going to pluck that electron right off cesium. And then cesium's going to drop to about half its size, and then fluorine's going to double in size. And this might be one of the exceptions to my rule. My rule was that the cations are smaller than the anions, but in this case, cesium being so big, it might still be bigger than fluoride. And so we'll make cesium plus and fluoride minus. And so in terms of Lewis symbols, we do it like this. Cesium has 1 valence electron. Fluorine has 7 valence electrons. Fluorine wants 1 more valence electron. So what's going to happen is fluorine's going to come over here and then just take the electron from cesium. Well, that's easy enough to do because cesium has a fairly low ionization energy. So cesium's going to lose that. And so we'll just draw the Lewis dot symbol like this. There's no dots around cesium. And then fluorine's going to have 8 dots. 4 pairs, call it 4 lone pairs, like that. That'll be it. And this shows the ionic bond. So this would be the structure for this. But what happens if the opponent is a little bit stronger than cesium? What's harder to oxidize? One thing that's harder to oxidize than cesium would be hydrogen. Hydrogen would be kind of a bit harder for fluorine to take. The ionization energy of cesium is less than 500 kilojoules. So it costs you like $500. And so let's say in terms of a money analogy, so it costs you $500, but you get the money back because we form the lattice, which is quite stable. However, to oxidize hydrogen is going to cost you $2,000. 500 versus 2,000. 2,000 is a lot harder. Fluorine can't quite do it. And so fluorine tries, but it is unable to take the electron completely in this case. And we form HF like this.
So it's a covalent bond?
Yeah, this is a covalent bond. This is a polar covalent bond. And so when we do this, what happens is we have the 1s orbital, and then we have a 2p orbital. 2p orbital is quite a bit bigger. I should try to draw it bigger. Then we have 1 electron in the 1s orbital like this, and 1 electron in the 2p orbital like this. And then what we're going to do is we're just going to kind of overlap these here. And so the 1s, this is what we call a 1s 2p sigma bond. Sigma has this Greek symbol here. And what we end up with is greater density of dots between the 2 nuclei here, this low. And that's what's going to hold the 2 nuclei together. The 2 nuclei, let's center 1 in the middle of this 1s orbital and 1 right in the middle of this 2p orbital. So you can see that. However, when we look at it, it's not shared evenly. It's an uneven sharing. And so let's do that with dots over here. So for example, there's no sharing at all here. This fluorine has taken the electron cloud, taking the electrons.
It's an ionic bond.
That's an ionic bond. But over here, the hydrogen, even though it's weaker than fluorine, it doesn't completely let go. So we get is this asymmetric, not a symmetric distribution. And so that means the electron, even though it's not completely over on fluorine, the cloud has definitely been distorted, that the electron spends more time around fluorine than around hydrogen here. And so I could try to show that here. You know, there is additional overlap, but the electron's going to spend more time closer to fluorine than to hydrogen out here. Now, what results is what we call a partial charge here. And so what happens here is we get a partial negative. A partial negative is called delta. This is the lowercase symbol for delta. This delta means partial. Partially negative. And over here, this is delta positive. So if the fluorine were successful in oxidizing the hydrogen completely, that is taking that electron, it would have formed fluoride, which has a full negative charge, not a partial negative charge. And then hydrogen would have had a full positive charge like cesium. So these are full charges.
That'd be like a triangle? Or,
I'm sorry?
uppercase delta?
Huh?
Would it be uppercase delta?
Uppercase delta would be the triangle.
So that would be the rotation flow chart.
Yeah. And so there's still sharing going on here. So ionic bonds, winner take all. Who's the winner in this case? Fluorine. So winner takes all. In a covalent bond here, we have some sharing. And in this case, we have some partial sharing of the electrons. Now, if we had fluorine in a tug of war with fluorine, then there's going to be no winner. But in this case, I shouldn't say that because it's a win-win type situation. A win-win type situation in which the two fluorines end up sharing. In order to achieve the octet. So in this case, it's much, or even, the electron's not going to be around one fluorine more than the other. Over time, it's going to be around both fluorines. And so this is what we call a symmetric electron cloud. This is an asymmetric electron cloud here. Symmetric. And we just have two of these p orbitals overlapping. This. I just tilted it a little bit because of the angle. And then we have this increased electron density here between it. This is what we call a 2p sigma bond. And so the name just comes from a 2p on this fluorine overlapping with a 2p on this fluorine, and the overlap is in the internuclear axis, within the internuclear axis, so that's sigma.
What if the pi bond has a layer?
Pi bond would be a possibility, but pi bonds would be weaker, and so it's much better to do a sigma than a pi, and in this case we can do a sigma, and so we'll do the sigma. Although you could have done a pi, it just would have been weaker and it wouldn't have lasted. Be replaced by sigma. So those are the three scenarios. These three scenarios are shown here. Here, it was able to completely oxidize it. It's a winner take all. Here we have two levels of sharing. We have the completely even sharing here and the non-even sharing here, where Y is stronger, because it gets more of the electron cloud, and X is weaker. Here are the two of X's, of course, are the same strength.
Can you just put non-polar and ionic bond?
Yeah, no, there's no non-polar ionic bonds. Ionic bond is the most polar. And so we go from zero polarity to the greatest polarity. And so this is non-polar, we call it. This is polar covalent, which is medium polarity. And ionic is the most polar. Polar, when we're talking about polarity, we're talking about separation of charge, like a positive and negative here. And so this would be the most polar. And when we think about a pole, we have electric poles and magnetic poles. And when we think about magnetic poles, we think about the Earth's magnetic field, which is a dipole. It has a north pole and a south pole. When we think about electric poles, you know, electric dipoles, di just means two. An electric dipole is going to have a positive and a negative end, and that's what we call a dipole. And so we could have that, or a partial positive and a partial negative, or we use an arrow to indicate this. The arrow points at the negative and the tail is positive. And so these are electric dipoles. The biggest dipole is going to be the ionic bond. And then this, the polar covalent, and the nonpolar has no dipole. No or negligible dipole. And so here we could just see the dipole increasing, polarities increasing as we go left to right. We have to define another characteristic that should have been defined in chapter 10, but it wasn't. And I talked about electron affinity. There's something that sounds very similar to it called electronegativity. Electronegativity is the ability to attract electron. Not just electron pairs, just electrons or electron to itself. Fluorine is the most electronegative, and we look at Pauling. You know Linus Pauling? Linus Pauling is probably most famous for his vitamin C. You know, he recommended people take 1,000 milligrams of vitamin C. You heard that? Or maybe it was even more. Like 1,000 milligrams is a gram of vitamin C every day. So he was very famous for that. But he's also a pretty famous chemist or physicist. And a bunch of stuff he's done. But one of the things he did was come up with the Pauling's electronegative scale. So 4.0 is the highest. And then the lowest would be like cesium or francium. This is like 0.7. And so electronegativities range from 0.7 to 4.0. So we have increasing electronegativity. The noble gases have no electronegativity. They don't want to attract any electrons to themselves.
What is it called?
Pauling's electronegativities. Not just Pauling, but other people did it, but the Paulings are the simplest. They're the simplest, but they're not the most useful, maybe. There are other electronegativity tables that some people might find more useful.
What is your concern with francium?
Francium being radioactive, pretty much ignore it from now on. Oh, you're right, francium. Cesium's 0.8. Let me go back. Let me cross that out, francium. But let me put the asterisk here. And so electronegativities are going to run from 0.7 to 4.0. 0.7 for the least francium, 4.0 for the highest fluorine. This is an electronegativity table here. You can see that the alkali metals have very low electronegativity, 0.7, 0.8, 0.8, 0.8, 0.9, and 1.0. And the nonmetals over here, the halogens are going to have the highest, 4.0. Actually, what are the three most? The three most is kind of mixed up, but
Fluorine, oxygen, and chlorine?
yeah, it looks like fluorine, oxygen, chlorine, nitrogen, and bromine look like a tie. But these are a little bit tricky because we can't go off the number alone. We also have to go off the sides. So if it's a tie between bromine and nitrogen, who do you think would win? Nitrogen, because of its smaller size. You know, when we gain electrons, smaller size is better. Except not too small. So for example, fluorine has the highest electronegativity, which means it has the strongest attraction for electron. However, which element has the highest electron affinity? Chlorine. And that's because fluorine's 2p orbitals are really small, and it's crowded, whereas chlorine can accommodate. So chlorine can't attract electrons as strongly as fluorine, but it can more easily accommodate it. So electron affinity is highest for chlorine. But normally we don't really care too much about that. That's just a weird exception. What we care most about is electronegativity. Fluorine being the most electronegative makes sense because it's the strongest oxidizer on the periodic table. Now, we have some very simple rules for bonds. You know, this is like a tug of war. 3.4 is strong. The strongest is 4.0. This is a 3.4 match, tug of war match between a 3.4 and a 1.2. Who's going to win? 3.4 is going to win. A 2.6 versus a 2.2. 2.6 is going to win. But we see that the bigger the difference in electronegativity, the more lopsided the tug of war is. And so what we're going to do is we're going to come up with some very broad generalizations. And so 0.4 is considered small. So if we have electronegativity difference, this is considered small. And so what we do is this is delta. This is the big delta, delta En. This is equal to delta En. The difference in electronegativity between the two atoms. Hydrogen, which one do you think hydrogen is? The 3.4 or the 1.2? The 1.2 actually. And the oxygen is a 3.4. So the difference between oxygen 3.4, which is fairly high, and hydrogen, which is fairly low, is 1.2. Yeah. This would be the delta En between carbon and hydrogen.
Isn't it 2.2?
You're right. That's wrong, huh? This is 3.4 minus 1.2 shouldn't be 1.2. It should be 2.2. That's correct. And then this one is what's the biggest we can have? Delta En. So you take the most electronegative. Which one's the most electronegative? Fluorine at 4 point and? Oops. And the smallest would be francium, 0.7. So the difference would be 3.3. And what's the smallest difference we can have? Like a 4.0 minus a 4.0. That would be 0. So the biggest delta En is 3.3, the smallest is 0. All right, I forgot to take the break. Let's take the break now. So the range of delta ENs goes from 0 to the smallest up to 3.3 for the biggest. At 0, we have nonpolar. At 3.3, we have ionic. It's the most polar. And in between, we have polar covalent. And so there's going to be some kind of dividing line here between the covalent and the ionic. And the nonpolar, you know, even if it's just a hair polar, would you still consider it polar or would you consider it non-polar? And so delta En of like 0.4 is still considered quite small, that we pretty much put that in the non-polar range. So non-polar ranges from about 0 to about 0.4. And then polar will range from about 0.5 to, I don't know, 2 point, well, this is 2.2, this is polar covalent. So this is not a firm cutoff, 2 or 2.5. And then ionic will be greater than this, 2 or 2.5. These are kind of fuzzy boundaries. These aren't strict lines here, just kind of fuzzy boundaries. And so these are more like rules. These aren't laws here. And unfortunately, there are going to be exceptions to the rules. Anyway, we're just trying to take a spectrum and divide it into 3 colors. If you take the whole visible spectrum and you divide it into 3 colors, what colors would you divide it into? Well, white would just be would be the combination of all the colors of the rainbow, but red, yeah, black would be absorbing all colors. Red, blue, yellow. If you were to describe all the colors of the rainbow with those 3, is it possible? I mean, so we're just dividing this. And so what would probably be better is like percent, rather than dividing it into 3 categories. We have a variety of categories. And so, like, for example, in Chem 1A, we do something called percent ionic and percent covalent character. And then we divide it, like 3.3 would be what's considered 100% ionic. And 0 would be 100% covalent. And so 100% ionic. And then at a 0 would be 100% covalent. And then we'd kind of divide it. And so it'd be 0% ionic. And over here, it'd be 100% ionic, but 0% covalent. And this would give us a more continuous spectrum than just trying to put it into 3 categories, small, medium, large. If all bonds came in only 3 sizes, then we would be fine. Well, there are 3 sizes of bonds here. We have the single, double, and the triple bond. These are covalent bonds. And it depends. Like, for example, oxygen wants 2. Each oxygen wants 2. And so what we say for oxygen is it should form a double bond. Oxygen has 6 valence electrons, and it can achieve an octet if it shares 2. So this is what we expect for oxygen. We expect to share altogether 4. Like this. Double bond expected. Nitrogen wants 3. So they're going to get in a tug of war for 3 electrons, and what's going to result is 3 pairs of electrons shared between them and 1 lone pair. Triple bonds are quite strong. About 1,000 kilojoules per mole. Meaning that that bond is hard to break. And this is the amount of energy it takes to break that bond, a mole of the bond is 1,000 kilojoules. Oxygen can get an octet in other ways too. So for example, if it doesn't bond with another oxygen, it can bond to 2 hydrogens and form water like this. And nitrogen can get to an octet by bonding with hydrogen as well to form ammonia. So here we have water and ammonia formed. And so oxygen can get 2 single bonds or 1 double bond. Ammonia could get 3 single bonds, or it could get 1 double and 1 single, or it could get 1 triple. And that will give it an octet. Sometimes there's some weird things that happen with the octet. So these are some exceptions to the octet rule. Nitrogen has 5 electrons, and oxygen has 6 electrons, and we end up with 11 electrons here. It's an odd number of electrons. When we have an odd number of electrons, one of the electrons is going to be alone. And that electron that's alone we call a radical. And so these are called free radicals. Free radicals are going to have this single electron here. You see it here. Single electron. Those single electrons we call like dangling bonds. They're reactive. Free radicals are reactive because they want another electron. Want 1 more electron. Electron there. And so these are odd number of electrons. Odd number. You got odd electron. It's odd number of electrons. Well, we have more than an octet. Atoms in the 3rd period and higher so the hypothesis here goes like this. 3rd period if you do 3s, you have 3p. I'll draw boxes for these. And then what comes after 3p? 4s. And then after 4s? 3d. And then after 3d? 4p. So when we're in the 3rd period or the 3rd shell, we're here. And what happens is that there's an empty 3d up here. You'd think there's an empty 4s. Well, what can happen is extra electrons may go up here. Why not the 4s? Not the 4s because of the distance, the size constraints. So it turns out we don't go here. So let me put an X through that. And so once we fill up the octet on a 3s3p, then we have these 3d orbitals that aren't too far away distance-wise, dimensions-wise, that we can put extra electrons in. And so what they're saying is that, okay, maybe some extra electrons can go in the fourth shell. And so third and fourth shell. So something like phosphorus, we only need 8 electrons to fill its octet, that is the third shell. But in this case we have 2, we count each line as 2. And so when I look at how many electrons I have here, I count 2, 4, 6, 8, 10. There's 10 electrons here. So if there are 10 electrons, I need 8 to fill up my third shell. And then I need 2 more up here in the 3D. So this gives us 10 electrons here. Sulfur here, this has 2, 4, 6, 8, 10, 12 electrons. And so that means I'll need 2 more pairs of electrons in the 3D. And so this is the hypothesis. And there's an alternate hypothesis for this. There's an alternate. In the alternate hypothesis, the octet rule is not violated. So it's more than a rule, it's more like a law. The octet law is not violated. That is, once you fill up this shell, the electron's not going up here, it's just too unstable. And so then how do you accommodate this? There are other ways of accommodating this, but that's Chem 1A. It's more advanced. We don't want to talk about it here. So these are called expanded octets. PF5, SF6. Phosphorus pentafluoride and sulfur hexafluoride are 2 examples of expanded octets. Or so goes the one hypothesis. The other hypothesis is octet is satisfying. These are less than an octet. Less than an octet aren't happy. And so BEF2, that only has 4, 2, 4. It doesn't quite fill up its shell. Boron, 2, 4, 6. So this is 6 electrons. This is 4 electrons. So we're quite, this one's 2 electrons shy, this one's 4 electrons shy, filling the octet. Sometimes we try to form multiple bonds, like with oxygen, we form multiple bonds. So for example, boron, we could fix that. If we do a double bond here, we do a double bond by taking one of the pairs, like the fluorine has 3 lone pairs, so why not just give one of the lone pairs to boron, but not completely let go of it. Still got 2 lone pairs. So now boron has an octet because when I count a double bond, it's 4 electrons, 2, 4, 6, 8. But the fluorine, what happened to the fluorine? Did the fluorine lose it? No, the fluorine did not lose it because it's still 2, 4, 6, 8. So this fluorine has an octet, this boron has an octet. It's a win-win situation. Or so you might think. It's a win-win situation, but fluorine will have none of it. Fluorine's not going to share extra. And so fluorine will not share extra lone pairs. What results is there are different ways we count the electrons. The lone pairs belong entirely to fluorine. And so this fluorine has 3 lone pairs. And those 6 electrons only belong to fluorine. However, the shared pair kind of belong to both. They belong to both boron and fluorine. And so essentially what fluorine is, if we share it 50-50, that is evenly split, then fluorine sacrifices 1 electron for boron, forming this double bond. It's not going to want to do that. It would rather keep it for itself. And that has to do with the electronegativity of fluorine. Fluorine is way too electronegative to do this. So fluorine will not share an extra lone pair. It's too electronegative. So that doesn't happen. So we just stuck. Boron's going to be the short end of this. Fluorine's going to be happy. Now, when we count the electrons, there are different ways we count the electrons. When we count the electrons for octet, we just count the total number around fluorine. So for example, I have 2, 4 from the lone pairs, 6, 8 from the bonding pairs here. And so I just count all the electrons around that atom. These lone pairs don't belong to that fluorine. So these fluorine lone pairs over here aren't counted up here, and this bond is not counted up here. It's just whatever surrounds that. The same thing with boron. I count 2, 4, 6, 8, and so it's the total number that surrounds it. That's called an octet, counting octets. But there's another way of counting electrons, and the other way of counting electrons is what belongs to electrons. So looking up here, I have 1, 2, 3, 4 that belong entirely to this fluorine, and then I have these that are shared. And what I do is I can just count half of those. So I get 1, 2, 3, 4, 5, 6. Over here, I count it, I get 1, 2, 3, 4, 5, 6, and then half of the shared electrons, which would be 7. So over here, fluorine ends up with 7 electrons. Over here, fluorine ends up with 6 electrons. Normally, fluorine is supposed to have 7 electrons. If fluorine ends up with 6 electrons, it's 1 electron short, which gives it a positive charge. Fluorine hates being positively charged. That's what we call formal charge. For oxygen, this is the failure of valence bond theory. This is one of the failures of valence bond theory. Valence bond theory, again, describes a bond as overlapping atomic orbitals. So it turns out this Lewis structure here is incorrect. Therefore, we must use the full version of quantum mechanics, which we call molecular orbital theory. To properly describe oxygen. And so this is actually, this is wrong. So why not just get rid of valence bond theory? You know, this is what we call quantum mechanics light. You know, like you get the light version rather than the full version. The valence bond theory is like the light version versus quantum mechanics full version, molecular orbital. And so why don't we just get rid of the light version and just use the full version? You know? It's easier. Yeah. The reason we don't get rid of the light version is it's so much easier than the full version. And therefore, for most stuff, it works okay. You know, it gives a decent representation of the. And so we don't completely get rid of it because it works okay and it gives us a good visual. It's a little bit off, but sometimes it's pretty close to correct. But you can do it with pencil and paper. Versus MO theory, you need to use a computer. And so, one of the failures of valence bond theories, you can use computers for valence bond too, but can do it with pencil and paper. MO it's impossible to do with pencil and paper. I'll just leave it at that. Are we going to do molecular orbital theory? No, we're not. This is going to be in Chem 1A. For now, we'll just use this. When you look at oxygen online, how do most people represent oxygen online? Most people represent oxygen online, the structure at least. Let's see. Like this. They're not showing the lone pairs, but most people will just draw out the Lewis structure, which is not entirely correct. So, this. They're not showing the lone pairs here. It's a shortcut method. Here they're showing the lone pairs. Here they're not showing the lone pairs, but all these are incorrect. This is very far from correct. Yeah. This kind of thing is people just looking at shells and that kind of stuff. Visualizing shells. There's no orbits. Then we have metallic bonds next. Metallic bonds have something called delocalized electrons. This is the electron sea. It's like the ocean. Alloys are mixtures, homogeneous mixtures of metals. This is electron sea model. And so the ocean is delocalized. That is, the ocean, like this electron doesn't belong just to this nucleus. This electron can move wherever it wants. That's called delocalization. If this electron were fixed onto this atom and it couldn't move, then that's called localized. The electrons are delocalized throughout the entire structure. So this would be like sodium metal, one valence electron. This would be like magnesium metal, two valence electrons. The valence electrons are free in the the ocean. However, the nuclei are kind of fixed here. The nuclei being the nucleus and the rest of the electrons, the inner shell core electrons. So that's what's being shown here. The nucleus plus the core electrons. These electrons are. Molecular orbital theory also describes metals. The bonding of metals is called band theory. And so MO applied to metals is called band theory. We don't use valence bond theory for this, so we don't look for overlapping atomic orbitals. Or we can, but they're all overlapping. Here are some common alloys. 18 karat gold is 75% gold. Well, but what we want to know is, we want to know how precise is that. Here it's only shown to 2 sig figs. I like a little higher precision, and if you can calculate a little higher precision, you should calculate a little higher precision. And so, for example, if you have a choice, then maybe at least go to 2 decimal places for the precision, or something like that would be good. And so, so for something like 18 karat gold, we'd like to be a little bit more precise. You know? Because if you just say 75%, what's the uncertainty in that range, 75%? I'd say the uncertainty ranges from maybe 74.5% to 75.4%. Well, let me, what did I do with it? Let me give back one more thing. So one of the things is, in your calculation for the ammonium nitrate composition, I wanted to see more sig figs. If you only wrote it like they have it written here, I mean, it's not wrong, but if you can be more precise, you should be more precise. They should be more precise in this particular one because we want to know what it is. I don't know what I did with that quiz. Forget it. Maybe it's exact. You know, it's the definition. So the closer you get to 75. But let's say somebody mixes it and they got 74.5%. Is 74.5% acceptable? It depends on how precise you are. Yes, it's acceptable because 74.5 would round to 75%. But you're missing 0.5% of gold. Well, here we have brass. There's lots of different compositions of brass, so that's why they give a range here. There should only be one composition of 18 karat, but obviously there's going to be range because it's hard to mix it exactly. And so there's going to be a little bit of range. We want to know how much wiggle room we have. For brass, we have lots of wiggle room. It's between 60 and 95% copper, then we can still call it brass. Bronze is a little tighter. You know, bronze should have 90% copper. Carbon steel, you know, lots of variety of carbon steel. Pewter, stainless steel. There are lots of compositions of stainless steel. Sterling silver. So those are some metals. It's easy to make alloys because all you do is you substitute. So here you might have a gold and then you put a silver instead of a gold. Or this may be copper, and then you put the carbon atom in there. Now, when we have alloys, they could substitute for a position like that, or they could, you know, if you have a small atom, they could go in between the big atoms here. So you can actually fit a small atom in here, rather than taking the place of one. If it's about the same size, then you have to take the place of one. And so we have different kinds of alloys. We have alloys that substitute for one of the existing atoms, and we have alloys that fit into these. Into these positions here are called interstices or holes. And so these are called interstitial alloys. But you don't have to worry about that. But I know that, like on the AP chemistry test, they talk about that kind of stuff a lot. Surprised me. So what we're going to do right now is we're going to look at structure, and then we'll try to get an idea of the shapes of these things, looking in chapter 13. So we're going to look at drawing Lewis structures of ionic species and covalent species. We're mainly going to focus on molecules, molecular compounds. And so there's going to be a set of rules here. When we draw the Lewis diagram, you don't have to write this down. We're going to do this over and over again, so it'll become easy. Step 1, count the total number of valence electrons. And so what we do is we look at all the atoms we have, and then we figure out how many total valence electrons. And then 1A, 1B, we adjust for the charge on ions. So for example, if it's negatively charged, it means it has extra. If it's positively charged, that means it's missing. And so we have to adjust it. Step 2, place the least electronegative atom in the center. This is just a rule. In general, that's usually what happens. The more electronegative elements go on the outside, the least go in the middle. Step 3, draw the tentative diagram, join atoms by single bonds. So this is for covalent, this is for molecules, this is not for ionic lattices. Step 4, step 3, B, let's say. 3A, draw the tentative diagram, draw 3B, join them by single bonds, 3C. Add unshared pairs to complete the octet around all atoms except hydrogen. Okay, what we do is we complete the octets to the outside, more electronegative elements first. And so complete the octets to the more electronegative elements first. Calculate the number of valence electrons in the tentative diagram and compare with the actual. If diagram has more, remove lone pair from central and terminal atoms and replace with additional bonding pairs. Repeat process till the number matches. Step 5, check the Lewis diagram. Hydrogen atom must have a duet, one bond, and all others should have a total of 4 electron pairs. And those 4 electron pairs can come in different scenarios, like, for example, a triple bond and a single bond, 2 double bonds, 4 single bonds. Have different. Okay, we're just going to go through these rules kind of fast and then just look at examples. So resonance structures and isomers. Resonance structures are 2 or more equivalent Lewis structures for a molecule or ion that are created by changing only the position of electrons in which the actual species is an average of resonance structures. So these, we have a choice. It can go between atoms A and B or atoms B and C. And they make equal structures. Well, those are called resonance forms. The resonance hybrid is the actual structure that is an average of 2 or more. So it's a hybrid of the individual structures. Then we have isomers, 2 compounds having the same molecular formula but different structure. Those are called isomers. We'll look at those as well. So these we're going to go through quite quickly here. So those are for drawing Lewis structures. And then we look at the shape using electron pair geometry or VESPER. So, when we look at these, we got to realize that pairs or groups of electrons have repulsion. And so this is called valence shell electron pair repulsion theory. And this gives us an idea of the geometry or the shape of things. And we have something called the electron pair angle or electron group. I'm not going to call them pairs. I'm going to call it groups. Electron pair or electron group angle. And the tetrahedron is just the geometric shape. This is kind of out of place. I don't know why Praglici does this so much. That's out of place, but we'll talk about tetrahedrons later. So we'll start thinking about the shape. The 2 things, when we draw Lewis structures, we don't really care about the 3-dimensional shape. But if we care about the three-dimensional shape, then we're going to take that Lewis structure and tweak it. So if I have two groups, to minimize the repulsion between two groups, we need to drop a 180-degree angle between the two groups. That's going to maximize the separation distance between them. And we end up with a linear group geometry here. If we have three groups, then the maximum separation will be given by 120-degree angles, and this is called trigonal planar. This is called linear. Trigonal planar arrangement of the groups will maximize the distance between the three. However, if we have four groups, then the maximum distance between four groups will be 109.5 degrees here. And so all the angles here are 109.5 degrees. And this is called a tetrahedral group geometry there. And so, look at that. We can use balloons to illustrate this. So this is linear group geometry with two balloons. It's going to have 180 maximum separation distance between two groups. If I put a third balloon in there, I'll end up with trigonal planar. This trigonal planar is going to have 120-degree angles between the three groups here. Again, this we're going to do a lot of examples of this. So don't have to write this stuff down again. Now, fourth group we can just bring on top of this. If we bring a fourth balloon here on top, it's going to push these three down. It looks like this. So this kind of looks like a tripod, three legs and shaft of the tripod. But all these are equivalent. So no matter which of these balloons you grab, it looks the same. And so if I grab that balloon and then bring that to the top, it looks exactly the same. And so all these positions are equivalent. And so all the angles are the same. And so it has this, what we call spherical symmetry. It's like a ball. Not quite a ball, but it's kind of like a ball or a sphere. It's got that kind of symmetry to it. So once we do our Lewis structures, then we can look at these. And then it gets a little bit more complex because what do these balloons consist of? If the balloons consist of single bonds, then we get that. If the balloons consist of single bonds and lone pairs, we get something different. And so this diagram we'll look at in more detail later. We try to draw things as three-dimensionally as possible. And we call that wedge dash diagrams. So we'll talk about this too. And we have molecular geometry. All right, so let's take a look at some examples here. We're going to look at NCl3 as an example of doing this. So the first thing we're going to do is just draw the Lewis structure following their rules that they have for the Lewis structures. Now, for Lewis structures, we need to figure out the valence electrons. So the valence electrons we just figure out from the periodic table. So group 1 has how many valence electrons? 1. Group 2? This is group 3. A has 3, 4, 6, 7, and finally an octet, 8. And so figuring out the number of valence electrons it should have, we just look at the periodic table. That tells us how many valence electrons it should have. So the examples we're going to do are some simple examples here. Let me back up here. So I don't care about the shape of this. I just want to do the Lewis structure. Okay, I don't know how I skipped those slides. For some reason I skipped these slides. So let's do ammonia. Ammonia, nitrogen has 5, hydrogen has 1. And so altogether I have 8. Hydrogen's less electronegative, but it can't go in the center. Hydrogen can only form one bond. Let's throw in some additional rules here. Hydrogen atom is never central. We call this a terminal. H and F can only form one bond. Therefore, these are never central atoms. All right, so the way I do it is, let's just do it from the very beginning. So if I'm given ammonia, NH3, to draw the Lewis structure out, I would start first with counting the valence electrons. Nitrogen has 5 electrons, and then hydrogen has 1, but we have 3 of them, so it's 3 times 1 electron. And that's going to give us 8 electrons. And then the next step is to build the skeleton. I can't put hydrogen in the center. That's the other rule. Hydrogen should go in the center because the least electronegative. The most electronegative is fluorine. And so the closer we get to fluorine, the more electronegative. Now, in terms of electronegativity, let's look at this previous chart. Where does hydrogen belong? Take a look carefully at this chart and tell me, where does hydrogen belong? Right above boron. Is this the same as boron? It's a little bit higher than boron, but it's a little bit lower than carbon. So hydrogen is kind of in the middle of the periodic table. And it's between boron and carbon, and so this is electronegativity. So hydrogen's electronegativity is due going 2, but nitrogen is a 3.0. Nitrogen's closer to fluorine, and the closer we get to fluorine, the more electronegative it is. And so hydrogen is less electronegative, and one of the rules in drawing Lewis structures is least electronegative goes in the center. But then there's another rule that supersedes that, and that is hydrogen can only form one bond, so it can never go in the center, because in the center you need to form more than one bond. If you're on the end, you can just form one bond. Yeah, so you throw the least electronegative, and there's another rule. The biggest atom goes in the center, because the biggest atom, if you have that in the center, then it can bond to more atoms without.
Which is priority? The size or the electronegativity?
Usually electronegativity and size go hand in hand. So they're consistent with one another. So here, unfortunately, there's no choice but to put nitrogen in the center, and then hydrogens are always terminal atoms. That is, they always end here. Now, if I count, how many electrons have I used up? Can you count how many electrons I've used up? 6 electrons. But I have a total of 8 electrons, so that means I have 2 more electrons. Now, where should I put the 2 more electrons? Normally you put them on the hydrogens because the terminal atoms get filled first. But what we do is we fill, or we complete the octet to the most electronegative first. What's the most electronegative? Nitrogen. And so we're going to complete that. And so we're going to take those 2 electrons and make a lone pair with the extra electrons. And so we end up with this. So this one gives us what we call as an octet around nitrogen. And each hydrogen has a duet. And so nitrogen has an octet, and hydrogen has a duet. And then we're good. It's like a good structure.
So nitrogen is more electronegative than hydrogen.
Yes, right. And so this is going to make what's called a polar covalent bond. If I look at the electron cloud with these two electrons here, the lone pair belongs entirely to nitrogen. And so that lone pair is right on top of the nitrogen. It doesn't have to be shared. But these ones have to be shared, so it kind of skews it. Nitrogen's stronger, so it's going to take more of the cloud. But hydrogen doesn't completely let go, because hydrogen has a little bit of strength. And so we're going to get a asymmetric electron cloud distribution to the bonds there. This is polar covalent. Let's figure out what delta En is for this. Nitrogen is a 3.0, hydrogen is a 2.2, so delta En is 0.8. Polar covalent. Now, when we do Lewis structures, your book doesn't go into it at this point, but we need to go into this.
Did you say that the electronegativity is 0.8?
The difference in electronegativity, delta En. The 3.0 is nitrogen, and the 2.2 is hydrogen. The difference between the nitrogen and hydrogen is 0.8, which means it's polar covalent. We have to learn the three ways we bookkeep for the electron. We count the octet duet. So this nitrogen has an octet, and these hydrogens have a duet. These lone pair belongs just to that nitrogen. The next way we count it is by a formal charge. Which one's stronger, nitrogen or hydrogen? So in reality, nitrogen's stronger, so it's shared unevenly. But when we do formal charge, we're going to assume it's shared evenly. And so 50-50 sharing just means it's a split. So these two electrons are not shared. And so those two electrons belong entirely to the nitrogen. However, we have one pair of electrons that forms a single bond to the hydrogen. And what we're going to do is we're going to assume that it's split evenly. So these two belong entirely to nitrogen, but these two, only half of them belong to nitrogen. The other half belong to hydrogen. Is that accurate? No, it's not accurate, but it's the way we're going to do it. And then we look at the other bonds and do the same exact thing. So each of the bonds, we're going to just go ahead and split them evenly. So how many electrons does nitrogen end up with? 5 electrons. How many does hydrogen end up with?
3. For each one, 4.
1. So the charge is the difference between what it has and what it's supposed to have. And so the charge is equal to what it's supposed to have. Minus the number of electrons in structure. So for example, how many valence electrons does nitrogen normally have? 5. How many does it have in this structure? 5. And so the charge is 0. Formal charges we circle. And so the formal charge here is 0. But normally we don't write 0 because there are a lot of 0 formal charges. Okay, this is for nitrogen. How about the hydrogen charge? Normal valence is 1. How many does it have in this structure?
1.
And therefore its formal charge is 0. So each hydrogen has a 0 formal charge. And the nitrogen is a 0 formal charge.
So usually the formal charge 0 update to rebalance it out.
Yeah, it's nicely balanced. A 0 formal charge is good. What's the opposite of 100% covalent? Yeah, right. The opposite of 100% covalent is 100% ionic. And so that comes up to number 3 here. The third way of counting electrons is by doing something called oxidation state. Oxidation state is the charge assuming the bonds are 100% ionic. In other words, winner take all. Who's the winner? The winner is the more electronegative species. So let's divide up the electrons again, but with the opposite assumption. If we divide up the electrons again, this lone pair here belongs entirely to the nitrogen. But here we have some shared electrons. Shared electrons belong to both nitrogen and hydrogen. However, we're going to assume winner take all. And so how many electrons does nitrogen end up with now? 8 electrons. And so the charge for nitrogen, in other words, we call it the oxidation state of nitrogen, is equal to its normal valence, 5 electrons, minus how many electrons it has in the structure, 8, minus 3. And that minus 3 we put in parentheses. So the oxidation state of nitrogen is minus 3, its preferred charge. But how many electrons does hydrogen end up with? The hydrogens end up with, no, not 1, none. And so the charge on hydrogen is equal to its normal valence minus how many ends up with this in the structure, 0. And so it's plus 1. And so the hydrogens are plus 1, nitrogen is minus 3. Now, in ammonia, is the bonding 100% covalent? No. Is it 100% ionic? No. It's somewhere in between. Somewhere in between we call polar covalent. And so this gives us the fourth way of doing it. Over here we call it partially ionic or partially covalent. I'll just call it partially ionic. And it's the polar covalent. This would be nonpolar. This would be extremely polar. This would be polar. Partially ionic. And so what we do here is it's not a full minus 3 on the nitrogen, and it's not a full plus 1 on the hydrogen. And so what we use is we use these symbols, delta minus on the nitrogen and delta plus on the hydrogen. So this is kind of what we talked about earlier. Delta minuses and delta plus. And so what we have is we have something in between the two extremes, 2 and 3. Now, even though 2 and 3 aren't always accurate, they're very useful for us. So do you guys want to take the nomenclature quiz today or Wednesday? Okay, if it's Wednesday, there's going to be a certain time limit. I don't know. It's the nomenclature is the same number, 40 plus. How much time do you need for that, you think? 30 minutes?
30, 40 minutes maybe.
All right. Yeah, well, then we'll do it Wednesday. All right. For redox, oxidation states are the most useful. Even though they aren't entirely accurate. And so if we look at ammonia here, what are the oxidation states? The oxidation states are -3 on nitrogen. And so what we say is that that's electron rich, -3. Ammonia should burn. And +1 on hydrogen. And what we do is we compare oxidation states. You can compare oxidation states with oxidation states. So these would be like say oranges. For acid base, sometimes the formal charge is most useful. For other applications, the other applications would be Lewis structure, stability, and Lewis acid base. Formal charge is more useful. So the formal charge on nitrogen is 0. On hydrogen, it's 0. On this hydrogen, it's 0. This hydrogen is 0. We'll call these apples. And so never compare apples to oranges because you're looking at different things. So, for example, is the charge on nitrogen -3 or is it 0? We don't compare apples to oranges. We compare oranges with oranges and apples with apples, but don't compare apples with oranges. These two charges represent two different things, and they're both very useful. The reality is this. The compromise between the two, we could say more accurate, but less useful in certain respects, but potentially less useful. The partial charges. So the charge between for nitrogen is between 0 and -3. I don't know what that is, so we're just going to call it delta minus. Delta minus is something between 0 and -3. And the charge on hydrogen is somewhere between 0 and +1. We're just going to call that delta plus. This is delta plus and delta plus. And so it's some number between these two extremes. We know what the limits are. You know, it's greater than 0 but less than -3. So it's within that constraint for nitrogen, and it's between 0 and +1 for hydrogen. And so we know what the limits are. but we don't know what the exact number is. We can figure out what the exact number is by using quantum mechanics to get an idea of what the charge is. But it's also useful for certain applications. But for redox, delta plus and delta minus aren't that useful, and formal charge is worthless. For redox, oxidation state is it. For other applications, oxidation state is worthless, and the other ones are worthwhile. And so we pick and choose which ones we want to do. All right, I just did that. Why don't you do this one for me? So once you're done with ammonium, do NH2 minus. Can anybody name this one?
I have written down all of them.
Nitrogen. No, that's for neutral. This would be nitrogen dihydride or something like that if it were neutral, or dihydrogen nitride. But this is an ion. Amide or amide. Discuss these here. So for ammonium, I would just go down the list. So for nitrogen, it's still 5 valence electrons, is in group 5. And then I have 4 hydrogens. Each hydrogen would be 1 valence electron. So that gives us a total of 9. However, I have a +1 charge. A +1 charge means we have to subtract 1 electron from the total. And so I have 9 minus 1, that gives me 8 electrons total here. Now, I can't put hydrogen in the center. Nitrogen has to go in the center, and then hydrogen has to be what we call terminal atoms. So what I'm going to do is I'm going to put nitrogen and then the 4 hydrogens attached to it like this. But when I count the electrons, I have 8 electrons here. How many electrons do I have here? 8. And so that's good because now I have an octet around nitrogen and I have duets around hydrogen. And so we're good. Now, as far as the charges go, well, this is the 3 ways of counting. The first way is octet duet, so we're set. Here. And so this is the first thing we always look for. We always look for the octet rule. And then the hydrogens have a duet. So the octet is good. Duet is good for hydrogen. Okay, the next way we look at this is by looking at the formal charge. So when we look at the formal charge, what I'm going to do is I'm going to split the bonding electrons in half. Not the electrons themselves, but the pair. Split it into singles. And so what that means is I'm going to slice the bonds in half here. If I slice the bonds in half, then that means one of the bonding electrons goes to this nitrogen and the other goes to the hydrogen. So how many electrons does nitrogen end up with? 4. How many is it supposed to have?
5 minus 4.
Yeah, right. It's going to be 5 minus 4, which gives us plus 1. And so its formal charge is plus 1. Now we don't, for formal charges, we don't usually write the 1. Let me redo this.
You just write E.
You just write, no, the positive symbol circled. And so normally for formal charge, we write it like this, plus the circle around it. That would be for the nitrogen. That was a positive. How about the hydrogens?
E1, E minus 1E.
1 minus 1 is 0, right? And so we end up with a structure that looks like this here. We need a positive charge on the nitrogen. And so, I'm not going to do it here. I'll do it over here. Now, this would be it here.
This is covalent. That.
It's covalent, but the bonds to the hydrogen are covalent. I can make an ionic or example. The bonds in this polyatomic ion are covalent. However, this polyatomic ion can ionically bond to an anion like this. And so within this, we have two types of bonds that are shown here. One, these are polar covalent bonds. And then two, this would be an ionic bond here. And so polyatomic ions like these have covalent bonds within the ion, but the polyatomic ion itself can ionically bond to other ions. So that would be it. So we have a positive charge. That positive charge, what we do is we sum up all the formal charges to get the net charge. So that's this out here. This is the net charge.
It would be N would be 1 times 1 gets charged, and H would be 4 of them times 0, which is 0.
We do it like this. We sum up all the formal charges, FCs. So this is plus 1, 0, 0, 0, 0 gives us plus 1. And so in this case, it would be plus 1 plus 0 plus 0 plus 0 plus 0, which gives us plus 1. All right, this is formal charge. Formal charges we circle. Okay, the third way we count the electrons is by oxidation state, OS, I'm going to call it. Here, winner takes all. So we have these 4 hydrogens attached here.
Nitrogen would have 8 of them.
Yeah, nitrogen would take all of them. The winner is a more electronegative species. So in this case, nitrogen ends up with how many electrons? 8. Right.
Would be, the formal charge would be 5 minus 8.
Yeah. The oxidation state would be 5 minus 8, which is negative 3. How about the hydrogens?
It would be positive 1.
Positive 1. Here we actually write the 1. Here we usually omit the zeros. So is nitrogen plus 1 or minus 3? Well, it depends on how you look at it and how we want it to react. It's both in this case. Because, you know, we're comparing apples and oranges. So this would be oxidation states here. So the oxidation state of nitrogen is minus 3, and the oxidation state of the hydrogens is plus 1. The last one is somewhere in between the two extremes. You know, this is the extreme on the left, this is the extreme on the right, or vice versa. And so what we want is we want some kind of compromise here. And so nitrogen's charge is going to be between +1 and -3. So it's going to be delta minus is what delta plus is. And that's what we end up with, the Lewis structure. In other words, the other way of doing this is not by looking at the two extremes. The other way of doing this is by looking at the polarization of the electron cloud. The electron clouds are going to be polarized towards nitrogen, making nitrogen negative. And so we see this asymmetric electron cloud here. Yeah. Ammonium, is it an acid or a base?
Ammonium is
Base.
It's a weak acid. Amide, do you know amide? Amide is a strong base.
well, weak acids have the positive charge and the base have the negative charge.
Yeah, basically. Acid-base properties are really going to be dictated by the formal charges and other considerations. Whereas redox is dictated by the oxidation state. So let's take a look at amide.
Just to say it again, acid base are dictated by charges, and redox is dictated by oxidation state.
Formal charges are very important in acid-base chemistry, but not in redox. In redox chemistry, oxidation state is most important. So nitrogen has 5 electrons. Hydrogen has 1, but we have 2 of them, so that's 2 times 1 electron. And then we have a -1 charge. -1 charge means extra electron or, yeah, it's going to be +1 electron, 1 extra electron. And so this is going to give us 8 electrons again. And we're going to throw the nitrogen in the center, like this. But if we throw the nitrogen in the center, how many electrons have we used so far? 4. And that means we have 4 more left over. I can't put the 4 more left over on the hydrogens. I have to put them on the nitrogen. And so this is the structure we end up with. 2 bonding pairs, 2 lone pairs. When I look at this structure here, we take a look. What is the formal charge on this nitrogen?
Formal charge is 5A minus
5 minus how many does it have? It has 2, 4, and then half of these.
6.
5,
I'm gonna say 6.
and then half of these, 6. So it has 6. So 5 minus 6 is -1. So the formal charge is negative. Here. Actually, let's do a different color. The formal charge.
For hydrogen, it'd be definitely.
Hydrogens would be 0. So we have a negative charge on the nitrogen. That's for sure. How about the oxidation state?
That would be -3 charge.
Yes. So the oxidation state is -3 on nitrogen and
+1 on hydrogen.
+1's on the hydrogen. That would be the oxidation state. Now, the net charge is the sum of the formal charges or the sum of the oxidation states. So if I sum up the formal charge, I have 0, -1, plus 0, which gives us -. If I sum up the oxidation states, I have +1, minus 3 is minus 2, plus 1 is minus 1. So the net charge in this case is the sum of the oxidation states.
Right above is the sum
Of the formal charges. It's going to be negative 1 because the 2 positives and the 2 no. All right. That's a net charge. And so, in other words, this is just an ion. It's the amide ion. And the amide ion, even though these are covalent bonds holding the hydrogens on there, this amide ion can ionically bond to things like a sodium ion. So if I have a sodium ion here, I can form sodium amide. This would be an ionic bond here, and I'd have a lattice. Within the amide ion, I have covalent bonds here, holding it together. And so this is sodium amide. All right, we're out of time here, so stop. Tomorrow we're continuing the titration lab. So.